I was talking about how we know what the Cartesian plane is. The Cartesian plane is basically the world where, the 2D world where we have two real number lines on top of each other laid up. And you can
Hmm.
basically pinpoint any point on this as a set of two real numbers, right? X and Y. However, complex numbers don't fit in this universe, right? So for complex numbers, we have a slightly different plane instead of the Cartesian axis, instead of the Cartesian system, we have the complex plane
Hmm.
because complex numbers are no longer purely real. They contain an imaginary part. Okay,
Okay.
it's pretty straightforward. We call it the Argand diagram. The Argand diagram is basically very similar to the Cartesian, you know,
Hmm.
coordinate system. It looks very similar too. The only difference is that any complex, remember that a complex number z in general can be written down as the sum of a real part and an imaginary part, right? So we
Hmm.
have a real part of z and then we have an imaginary part of z. So what we do is we say that, okay, let's put the real part of z as a number line on the x-axis, the horizontal axis, and the imaginary part of the complex number on the uh, y-axis, or the,
Hmm.
you know. So we now call this the imaginary axis and this the real axis instead of x and y.
Okay.
And honestly, it's pretty self-explanatory how you would put a complex number on this plane because imagine, for example, you have 3 plus 4i. The real part is 3 and the imaginary part is 4, so the complex number sits right there. So it
Okay.
basically functions exactly the same as a regular um,
Right.
uh, Cartesian axis. The
Okay.
now, of course, since we already have a bunch of fun tools to play with, like vectors, we can actually write down this guy, this complex number, as a position vector also. Okay, we
Hmm.
can call him equivalent to 3, 4, because it's a vector that goes 3 units to the right, I mean 3 units in the horizontal direction and 4 in the vertical direction. So we can
Right.
actually call it by a position vector also. Okay.
Hmm.
Now, let's call this basically O, Z. So this point is Z basically. Now,
Okay.
that's another way to kind of think about um, complex numbers on the Argand diagram. However, let's try to think about it a bit more. So now that we've put it on this kind of XY axis kind of situation, right? Maybe we can define some properties of a complex number from this. What do I mean? We can define the length of a complex number, which we call the modulus of it. So the modulus of a complex number is basically the length of its position vector. So how long is the position vector that like reaches the complex number essentially, basically this guy.
Okay.
And you can imagine that any point on this entire plane can have a vector drawn with it, right? From the origin to that
Hmm.
vector, you can get a line. And that line is whose length we're trying to find. Now, thankfully, the even though it looks different, even though we've named things differently, it still functions similarly to the xy axis. So
Hmm.
we can find the modulus of a complex number by simply using Pythagoras theorem, which is because we have a triangle whose horizontal and vertical sides we know. The vertical side is the imaginary part of the number, and the
Okay.
horizontal part is the real part of the number.
Hmm.
So the modulus or the length of the position vector of a complex number on the Argand diagram is simply Pythagoras theorem. Square the real part plus square the imaginary part and then square root the whole thing. Basically just, Pythagoras theorem.
Hmm.
So this is the imaginary axis, this is the real axis. So that's basically it. That's called the modulus of a complex number. Let's define one more thing about a complex number, which is which we call the argument of it.
Okay.
So you will see this in books sometime written as arg of z, basically. You might see that notation. It used to confuse me for a while, but it just means argument. And the definition of the argument is even more surprising. It sounds like it's going to be something really, complicated to understand.
Hmm.
But the argument of a the argument of a complex number is simply the angle that it has with the x-axis. This is called the argument of the complex number. Okay.
Okay. Hmm.
And it is denoted by, If I remember correctly, it's just called theta. So we normally call it just theta for a complex number. So for example, imagine that the complex number's real part is A and the
Mm-hmm.
complex number's imaginary part is B. In other words, the complex number itself is equal to A plus IB. Okay?
Right. Okay.
So if this is the complex number you have, we can, of course, we already know how to find the modulus of it, but we can find this angle by using a very simple rule, right angle triangles, right?
Mm-hmm.
We know the opposite side of the right angle triangle, and we know the adjacent side of the right angle triangle. So
Mm-hmm.
we can use tangent. Tangent of the argument of the complex number is simply equal to opposite over
Mm-hmm.
adjacent, which means that we can find the argument by just taking the arctan tan inverse of b over a.
Okay.
And if you want to be more, specific and you want to have the formula, b is the imaginary part of the thing, complex number,
Mm-hmm.
and a is the real part of the imaginary number. So this is the general formula to find the argument of a complex number. Why did we just do all that? Why did we learn about two very weird things,
Mm-hmm.
oddly specific things about complex numbers? The reason we did that is because we can also define a complex number other than defining it as a sum of a complex of an imaginary and a real part. We can also define it as its argument and its what's the word? Its modulus, which is like this. Z, any complex number can be written down as its modulus times e to the power of its argument, I times its argument. This is
Mm-hmm.
called Euler's formula or Euler's identity, and it's a very, very interesting thing in mathematics because if you think about it, by raising a real number to I, a complex number, and time multiplying it with an angle, and then multiplying it with a length, we get point in space, which is pretty crazy if you think about it a little bit. We
Yeah.
call this the modulus argument notation or form. Uh, I don't know, form, but it's also simply called the exponential form of a complex number,
Okay.
which is a bit easier on the mouth. I think yeah, that's a
Mm-hmm.
lot of words. So, I wanted to clarify something about the argument now. So, you know how I said that the angle that the complex number has with the x-axis is the argument? Maybe I lied a little bit because it's not exactly true. I mean, it is, but there is a little nuance to it. So, for example, let's do an example of a complex number. Let me think. It's gonna be no, yeah, -4 plus I6. Now, if you put this on the diagram, you'll see that it's somewhere over here,
Mm-hmm.
right? Now, is the angle supposed to be this one or this one? Which one's the argument, right? I mean,
Uh,
that's a pretty good
yeah.
question, right? I mean, which is it with the positive x-axis or is it just the angle with any of the axis?
Right.
So the thing is, we need to find the angle with um 1 second. Yeah, we have to find the angle with the positive real x-axis. So
Mm-hmm.
basically, we need to find this angle specifically. So it's not the
Yeah.
closest x-axis, but the positive side of it, basically, the positive
Mm-hmm.
side of the real axis. Okay. So
Okay.
how do we find this angle? It's not that tough because you can just find this angle first and then do pi minus that. Okay.
Right. Okay.
Yeah. So for instance, in this case, you can find out that the this angle, let's call it alpha, which is not the argument. We can
Mm-hmm.
find alpha by using, imaginary over real,
Yep.
right? By the way, I use the positive numbers directly. The reason
Okay.
is because I'm talking about lengths, right? Once
Mm.
I make the diagram, I can see what the direction is, so I don't need to use the negative version.
Okay.
I find alpha using this. Let's calculate what it becomes. Oh, remember to, by the way, do it in radians. This whole thing only works, like, it's only
Mm.
true for radians.
Okay.
0.9827. And if that is alpha, then the actual argument, so we can call it argument of z, is equal to pi minus 0.9827, which is
Mhm.
2.159.
Okay.
So that's the angle that we're looking for. Okay. So that
Got it.
was a little nuance I wanted to mention. Other than that, it's a pretty simple idea, I think. I mean, obviously, once you learn it in the beginning, it kind of looks like it's gonna grow up to be a very complicated thing, which it is.
Mhm.
But you don't need to worry about the complications of this thing yet. In your exams, most of the time, what you're going to be given is maybe a complex number with the imaginary part unknown, and they'll give you the modulus of it, and they'll like ask you to find them, the missing part,
Okay.
etc. Or they may give you a bunch of complex numbers and ask you to convert them to modulus argument form, stuff like that.
Okay.
I also want to talk about, so we've already talked about how to convert a complex number that's given in this form, and I don't know what this form is called. Um, it's called the Cartesian form. So this is called the Cartesian form, and this guy is called well, I'm not going to write it again, but it's called the modulus argument form. Okay.
Okay. Okay.
So you might be asked to convert the Cartesian form into the modulus argument form, which I've already shown you how to do. Again, R is simply the modulus of Z, which is simply the real part squared plus the imaginary part squared square root, and theta is simply tangent inverse of um imaginary over real. So these are like that's it basically.
Okay.
Okay.
Got it.
And so this is how you convert from the Cartesian form to the stuff that you need for the what's it called, the modulus argument
Okay.
form.
Okay.
But how do you do it back? How do you go back from the modulus argument form,
Mhm.
going from modulus, or let's call it the exponential form, to the Cartesian form? Let's think about it, right? So all you know in the exponential form is the length of the vectors r and theta, right? So
Mhm.
let's say that I tell you that a complex number is, I don't know, let's say 2e to the power of I pi, or pi over 3. Okay. That's
Okay.
my exponential form. The thing is, pi over 3 is somewhere around here, and we know that the length is 2, right?
Mhm.
So the angle is pi over 3, and the length is 2. What are we trying to find? We're trying to find the real, oh God, the real part, and we're trying to find the imaginary part. As you can see, it's a pretty simple question. You know two things about the right angle triangle, and you're
Yes.
trying to find the adjacent and the opposite sides. So how do you suggest I can find the adjacent side? Let's begin with that.
Okay. I can use sine pi over 3
Okay,
equals the imaginary part over 2.
exactly. Which shows you that the imaginary part is simply 2 times sine pi over 3, which is, by the way, in a general sense, r times sine of theta. So you can literally just, do that directly.
Right.
And the
Okay.
real part, for the real part, you can do cosine,
Mhm.
right? So real over 2, which gives you, again, that the real part is 2 times cosine pi over 3, which in a general sense is r times cosine of theta. See, r times
Yeah.
cosine theta. So what have we learned? That for a given um, exponential form complex number,
Mhm.
you can convert it to the Cartesian form by just doing r cosine theta, that's the real part,
Mhm.
plus I times r sine theta, that's the imaginary part. So this is how
Okay.
you can convert between both the forms. Super simple.
Got it.
Let's see if there's anything else left in this chapter to work on. Okay, so we've already talked about how, I think in the last class we already talked about how to prove that, a, well, to prove that a quadratic has only complex roots or, similar roots, etc. So in this chapter, we're also supposed to talk about how to solve equations and things you can learn about the equations without actually solving them. We already know about these things. Let me put them on the board. Um, So about solving equations and kind of tying that with complex numbers, we already know from earlier that if the discriminant in a quadratic equation is more than zero, if it's positive, we're going to have two real roots.
Mm-hmm.
However, if it's equal to zero, we're going to have two real but equal roots. They're going to be called repeated roots in that case. And if
Right.
it's less than zero, we say that it has no real roots.
Mm-hmm.
However, now, since we have a new kind of field of math that we know about, which is complex numbers, we can fully claim that if it's less than zero, it's not that we get no roots at all. It's just that we don't get any real roots. Our roots are now complex roots of the form x plus minus I. What does that mean? As I explained in the first class, they come in conjugates, right? So you have 2 plus I, you'll also have 2 minus I. That means that one root is the conjugate of the other root. For notation, by the way, this is kind of important. So if, for example, a complex number is z, his conjugate is noted by z with a little star on top of it. Star means conjugate. Okay. So for
Okay.
example, if z is 2 plus 3i, z star is automatically understood to be z minus 3, 2 minus 3i. Okay.
Right. Okay.
So this is about quadratic equations only, though. What about like more general equations? Um, the thing is, there's something called the fundamental theorem of algebra. So fundamental theorem of algebra states that an nth degree equation so has n roots. What does that mean? Nth degree equation means, for example, this is a second degree equation because the highest, oh, this is not an equation, now it is. This is a second degree equation because the highest power of x available is the second power. So, for example, if you have a cubic equation, you will always have three roots. However, those roots may be complex, or real. They may be a mix of both. However, whatever degree you have, that's how many roots you will get. Okay.
Okay. Got it.
That's like the fundamental theorem of calculus. Now, I don't know if you know I forgot what it's called. I believe it's called the factor theorem. So I'm kind of giving you a little bit of recap, by the way.
Okay.
So the factor theorem says that if you have a function, sorry, if you have a equation like ax cubed plus bx squared plus cx plus d equals 0 or so whatever,
Mm-hmm.
if x equals like I don't know alpha is a root of this equation, then um, a alpha cubed plus b alpha squared plus c alpha plus d will always equal 0. I mean, that's actually kind of obvious, isn't it?
Mm-hmm.
So in a general sense, if you have any function that equals 0 and you know that alpha is a root,
Mm-hmm.
then f of alpha will always be 0, meaning if you plug in the root as an input to your function, you will always get an equal to 0 in it.
Okay.
This is kind of hard to see without an example, so let's do a quick example for this. Um, I'm going to show you a complete example, something that could pop up in an exam too.
Okay.
Super important. Oh, it's big. One sec. Okay. The first part of this question is, so you have an equation given to you. Don't get thrown off by the fact that they have z's here, okay? That's
Okay.
just them kind of hinting to you that we're expecting complex solutions to this, but it's really unimportant. You could put x here too. Doesn't matter. Okay.
Got it.
Anyways, so you have an equation, and they're saying show that z equals 4 is a root of this equation.
Right.
How do we prove that? What do you think?
We can plug in the 4 for
Exactly.
Z.
hmm
Okay.
So when we plug in the 4 for z, we see whether we get 0 as a result of it. Do we get 0? Like that's basically a question at this point.
Mm-hmm.
I'm assuming we will. I guess we don't need to
Yeah.
work through this, but yeah, so it is a root.
Yes.
That's how you can prove it. Now for
Okay.
part B, it says that find all complex solutions of this cubic equation. Now the thing is, you don't know how to factorize a cubic equation. Now I don't either. Okay. It's not something you're supposed to know by hand, I don't think, at any point in your life.
Okay.
So what do we do? To solve a cubic equation, or really any equation whose factorization method you don't know by hand,
Mm-hmm.
your only kind of saving grace, I guess, could be that if you already know a root or a bunch of roots of that equation. Because see, we're expecting three roots to come out of this, right?
Mm-hmm.
Meaning we expect this to be broken down into three separate factors. because each factor gives me one root, z minus something, z
Yes.
minus something, z minus something. I do know one of them because I know that 4 is a root, so I can put the 4 here. That's where the 4 came from.
Okay.
But I don't know the other two, right? So what do we do? It might be tempting, hey, expand this and try to figure it out, but no, there's an easier way to do it.
Mm-hmm.
Look, do you agree that while I don't know what A and B are, for a fact, this must be equal to this? Otherwise, this everything I'm doing is pointless. If what I'm claiming is going to be the factorized version of my equation,
Mm-hmm.
I mean, if they're not equal, right? If the thing I have against the thing that I'm claiming is going to be the factorized version of it, if they're
Yeah.
not equal, then everything I'm doing is wrong. I should just
Yes.
give up on math. Then
Yeah.
what I'm going to do is I'm going to realize that since this guy contains each three of these components, why not divide this guy with z minus 4 and realize that the quadratic that I'm going to be left over with is going to be this stuff.
Mm-hmm.
So I'm going to basically take my entire expression and long divide it by the one factor I know is inside of it, meaning I know that this guy is fully divisible by z minus 4,
Mm-hmm.
right? So I remove it. I basically by dividing z minus 4, sorry, by dividing this by z minus 4, I am removing I'm removing z minus 4 from this list of components basically, right?
Right.
So that's what I do. So basically the general rule is that if you have an expression and you know a factor out of it, divide that expression by that factor, and you will be left over with a new expression that contains only the factors that you don't know of anymore. Okay,
Right.
that's basically what I'm saying. So let's
Right.
divide. Do you know how to do long division?
I do on the top, does that leave me with z squared? Because
Let's start with that. So z,
okay,
z squared, which leaves me with what here?
with z
Mm,
squared. Oh,
z
z.
cubed.
Okay.
Yeah,
Yes, and then minus z.
minus 4z squared.
Okay.
So basically what I'm doing is, let me remind you, I'm
Yeah.
trying to find something that I can multiply z with to make a z cube appear here. So I pick z squared.
Yes.
By picking z squared, I get z cube here. However, collateral damage. I multiply z squared with minus 4 and I get a minus 4z squared here too,
Okay.
right? So that's basically just, it has to happen because this was my goal. Why did I do that? Because in division, you're subtracting these two things from each other now.
Yes.
Now be very careful. Minus 3z squared minus negative 4z squared. Okay? Don't just go
Okay.
and do
Yes.
this without understanding. So minus 3z squared plus 4z squared would be 1z squared.
Right.
Okay. Now what do I multiply z minus 4 with to get, by the way, pull the rest of it down.
Mm-hmm.
Forget to. I've always, I've done situations where I've forgotten the last number. So
Okay.
now multiply z minus 4 with something that gives me a z square over here. That's what I want.
Just
But
z, right?
exactly.
Yeah.
So I do z square minus 4z, which leaves
Okay.
me with nothing here,
Mm-hmm.
and minus 3z plus 4z, which is
Yeah.
just z. The minus 4 comes back down because he didn't really take part in any of the.
Okay.
Finally, what do I multiply z minus 4 with to get z minus 4?
Just one.
Exactly.
Okay.
That leaves me with nothing, which proves two things. Number one, z minus 4 indeed was a factor of this stuff because I
Right.
got no remainder. I got
Yes.
no remainder, which means that this guy goes fully into z cubed minus 3z squared minus 3z minus 4. And secondly, I found out that when I remove this guy, the remaining part of this guy is
Mm.
just z squared plus z plus 1. You see
Right.
what I mean? So
Yes.
this stuff is just z squared plus z plus 1. That's what I've proven. Okay.
Okay. Mm-hmm.
So I really just need to factorize this and find this guy's factors or roots, sorry.
Right.
So there's a bunch of ways to do that. You can use quadratic formula. I like to use this completing the square method. It
Yes.
always works. So
Mm-hmm.
z plus this is
Half
1, so this would be 1 over 2. Good. Go on.
plus or minus half
Mhm.
squared plus one.
Exactly. Good.
Mm-hmm.
So we have z plus 1 over 2 whole squared minus 3 over, no, plus 3 over 4
Mm-hmm.
equals 0.
Mm-hmm.
Now here's where the fun begins. We have z plus 1 over 2 whole squared equals negative 3 over 4.
Yes.
Now when we square root this, it'll tell us why they've been putting z in place of x over here,
Mhm.
because we have a negative square root. And remember that a negative square root can be just replaced with I times the positive version of itself directly. That's a
Yes.
shortcut, but in my first class, I kind of showed you why this happens.
Mm-hmm.
Finally, we've square rooted already. Finally, we can subtract 1 over 2 from both sides and get our conjugate pair of our second and third factors that we were looking for.
Okay.
Minus 1 over 2 plus this and minus this. Those are
Mm-hmm.
the two other roots in my cubic. Just as expected, two more roots have been found. Technically, I'm cheating because complex numbers always come in pairs, but
Mm-hmm.
that's not my fault. I was only expecting two roots, two
Mm-hmm.
more roots, and I got them.
Okay.
Um, okay.
Got it.
So here's an interesting thing that, you really have to kind of find it out on your own. But think about it for 1 second and you'll realize it. See, I'm gonna say two sentences. Cubic equations, since they're cubic, have three roots, right?
Mm-hmm.
So they always have three roots. Okay, that's
Yep.
one thing. The second thing is complex roots always come in pairs. They cannot come in singles ever. It's impossible. So if cubic equations always have three roots and complex roots always come in pairs, then a cubic must always have at least one real root. Think about
Okay.
it. Because you couldn't fill a complex root here because then you would need his cousin to tag along. But since it's a cubic, you can't have a fourth root. So you're going
Mm.
to need always one real root.
Right.
You see what I mean? It's
Mm-hmm.
almost like a riddle because
Yeah.
it's impossible for both of those things to be true at the same time. You cannot have three complex roots because you always need an even number of complex roots because they come in pairs. So a cubic must have one real root always. And this is very easy to see if you think about what a cubic graph looks like. A cubic graph will always have a peak and a minimum and then go back the opposite direction, right? So
Okay.
you cannot exhibit that behavior without cutting the x-axis at least once.
Mm-hmm.
Like, because, you could do this, but you'll have to touch once at least because you have to go minus infinity, right? Or
Yes.
you could do this. Um, in this case, again, you'll have to cut once. That is why we always expect one real root.
Okay.
And that's basically it. So I believe that finishes our discussion of
Complex numbers.
uh-huh,
Okay.
maybe okay. Okay. So there's one more idea, which is another like basically another way to play with complex numbers. Oh, okay, there's a few more things actually we have to discuss.
Okay.
Another thing is finding roots of complex numbers. So what if you have a complex number and you want to find its square root? That's a weird thing to do, but you might have to do it in a problem, basically incorporate it into a problem. So let's
Okay.
take a look. So we need to find the square roots of this complex number and then go on to find show the position of the roots on the Argand diagram. So here's how you do it. First, let's write down what we're trying to find. We are trying to find the root of this guy, and it's going to obviously be a complex number, right?
Okay.
So we're trying to find x plus I y. We're trying to find what x and y are. Okay, let's square both sides. So treat it like an equation basically now. So square both sides. So x plus I y whole squared. Open up the right side. 2, let's call it I 2xy
Mm-hmm.
plus, oh no, minus y squared. Because if you have plus I y whole squared, the I squaring will make it -1, and squaring the y just makes it y squared, which makes the whole thing minus I y squared.
Okay.
Do you agree? Oh no, minus y squared, sorry. Because the I is gone. When you square the I, it just becomes -1.
Okay.
Okay.
Mm-hmm.
Now, we have -2 minus 2 lambda, sorry, root 3 I equals x squared minus y square plus I times 2xy. So I'm basically just writing this and this part, the real parts of this with no i's in them combined, and the I part on the right. Do you agree?
Yes. Okay.
Okay. And the reason I did this is because now I'm going to conclude that x square minus y square must be equal to negative 2,
Mm-hmm.
and 2xy must be equal to negative 2 root 3,
Okay.
right? Now that I have this, my only job is to. So, did you understand everything so far? This
Yes.
claim is just me basically saying that this is what I'm trying to find, and this is what I expect it to be in the form of. Then I'm just trying to basically solve the equation for x and y.
Right.
Now I have two equations, and they are just regular simultaneous equations. I just need to solve them simultaneously. So using
Mhm.
the second equation, I can claim that y is equal to negative 2 root 3 over 2x,
Yes.
which means I can cancel out the 2's, negative root 3 over x, which means y is just equal to negative root 3 over x. I'll
Okay.
plug this definition of y into the first equation.
Mm-hmm.
By the way, I'm sorry if I'm going too fast. Let me know if you need me to like slow
No,
down.
I'm getting everything
All
so
right,
far.
perfect.
Hmm.
This is what you have, and now you have x squared minus 3 over x squared equals negative 2,
Right.
if I'm correct. Yeah. So now, finally, we can maybe multiply everything by x squared there, and then move everything to one side of the equation.
Mm-hmm.
And now, okay, another little layer of complexity comes in, which
Mm-hmm.
is where you have to realize that this is a quartic equation, of course, quartic because the highest power of x is 4. However,
Mm-hmm.
it can be modeled as a quadratic equation also.
Yes.
As you can see, you have something squared plus something.
Mm-hmm.
Oh, oops. Plus some 2 times something minus 3 equals 0. So if
Yes.
you say let, for example, I don't know, y be, no, not y already exists in this problem.
Mm-hmm.
Let, I don't know, t be x squared, then this
Mm-hmm.
equation looks like t squared plus 2t minus 3 equals 0.
Yes.
And by solving this quadratic equation, we will get two answers, negative 3 and 1,
Okay.
which means that x squared is negative 3 and x squared is 1,
Mm-hmm.
which means that x is I root 3, or because you have the root of
Yeah.
negative 3, which means I root 3,
Mm-hmm.
or x is plus or minus 1. This is also actually plus or minus, I just realized.
Okay.
Whenever you square root something, always make sure you put the plus and the minus form of it.
Okay.
And you have four answers now, actually. So with these four answers, finally, we can find y. What is y? Earlier, we said that y is negative root 3 over x.
Mm-hmm.
So y is negative root 3 over x, which means that you have a bunch of choices for y now. The first
Mm-hmm.
choice is minus root 3 over I times root 3, or plus minus I times root 3. Okay,
Mm-hmm.
which means that the root 3's cancel out, gives you negative 1 over plus minus I, which
Okay.
basically, so if you think about this, you have minus 1 over plus I and
Mm.
minus 1 over minus I. So if you think about it, it's essentially, negative of 1 over I or positive of 1 over I.
Okay.
So what I'm trying to say is that you can rewrite it as just 1 plus minus 1 over I,
Okay.
right? Because you have two choices anyway, ultimately.
Mm-hmm.
But of course, you can think about them as separate choices too. So that's your first answer. Ah, okay, I just realized. So if you come back here, you'll realize that x is the real part. X cannot be imaginary,
Right.
right? I mean, we picked
Ah.
x to be the real part. So we should have discarded the imaginary part because how could x,
Yeah.
the real part, be imaginary? Then that would defeat the whole purpose.
Okay.
So this was actually not useful at all.
Yeah.
So we should discard. So I kind of got too far in the flow, but x can't
Yeah.
be imaginary. It wouldn't make sense for the real part to be imaginary.
Right.
So which means that y can only be minus root 3 over plus 1 or minus root 3 over minus 1. And as I said, both of these are the same. I mean, you can write them combined as plus minus root 3.
Okay.
So that is why. Now, of course, long question can pop up. I don't think I've seen this often in exams,
Mm-hmm.
but a question like this may pop up randomly, and you'll be one of the maybe 30, 40% that'll know how to solve it.
Okay.
Clearly, it's a very specific method to solve it. The starting is interesting, but
Yes.
useful to know.
Okay.
Okie dokie. So next up, and I believe this is the last idea.
Mm-hmm.
It's not part of the question you're doing, and I haven't seen questions of this idea basically in past papers in a while, but
Okay.
it is a thing that you should be familiar with. It's basically called loci.
Mm.
Let's write this down. So let me maybe I should make this in a separate recording. One second.